Chapter 13, Solutions. So let's think about what a solution is made up of. So a really good example is salt water, seawater, right? So what is salt water made up of? You have the solution, which is the salt water, and it's a homogeneous mixture of salt and water. Now, it's homogeneous because when you're looking at a glass of salt water, you don't see the salt in the water. Since salt is aqueous, it is dissolved into the water. But salt is still there and water is still there. So you have a solution that is made up of a solvent and a solute, where the solute is what is being dissolved and the solvent is a substance it's being dissolved in. So there's many different types of solutions. So a solution can be a solid in a liquid, it can be a gas in a liquid, it can be two different kind of liquids, two different gases, a bunch of different combinations. And in aqueous solutions, water is the solvent, and a solid, liquid, or gas is always the solute. So any aqueous solution, you always know that water will be the solvent. So for example, ethyl alcohol is a solute that usually mixes with water to form a solution. And that's a liquid. Salt water usually forms with water, where salt, NaCl, is the salt. Another example would be carbon dioxide, which is a solute, and that's a gas that usually dissolves in water to form aqueous solutions known as club soda, for example. So all different types of aqueous reactions possible, solid, liquids, or gases in water. Now, that doesn't mean that any solvent is going to dissolve all types of solute. There's some regulations to that. So solvents don't dissolve all possible solutes. For example, if you have grease, you can't really clean it with water because grease is insoluble. So the solubility, how much something can dissolve of a substance, is the amount of the substance that will dissolve in a given amount of solvent. So for example, for NaCl, sodium chloride, at 25 degrees Celsius, we can dissolve 36 grams of sodium chloride in 100 grams of water. So if you have, for example, 50 grams of sodium chloride and you want to place it into a beaker of water that has 100 grams in it and it's at 25 degrees Celsius, only 36 of that amount will dissolve. The remaining 14 will not dissolve. So different salts have these solubilities known so that you can always measure out the exact amount for a given solvent, water specifically, at a temperature that you can dissolve and it be soluble. Now, comparing that to grease, since we know sodium chloride is usually soluble, the solubility of grease in water is actually almost zero. So the solubility of one substance in another depends on two things. So it depends on the tendency to go towards mixing, and it depends on the types of intermolecular forces. So we talked about the intermolecular forces within a liquid, within a gas, within a solid. Now, if we're putting a liquid and a solid together, they have to overcome the intermolecular forces to mix. And they have to go towards mixing. So those are two factors important when we're thinking of the solubility of substances. This brings us up to entropy. So entropy means going towards a disorder, essentially. So far, we've seen that many physical systems tend to lower potential energy. So if you have two particles with opposite charges, we know that a proton and an electron, or a cation and an anion, like we've learned in the previous chapters, if they move towards each other, they're happier because they lower their potential energy. So they go towards mixing, the proton and the electron, or the cation and the anion, because as they mix together, they lower their potential energy. This is what we've learned through our Coulomb's law. So in the formation of a solution, does not necessarily lower the potential energy of its particles. If you think of the formation of a homogeneous mixture of two ideal gases, suppose that we enclose neon and argon into a container. with a removable barrier. Now, first you have your neon gas and your argon gas, and they're not mixing because you have this little barrier right here in between. Well, as soon as you lift the barrier, there's nothing keeping those gas particles from one another. So they can mix together to form a solution. So at low pressures and moderate temperatures, both neon and argon behave as ideal gases. So they do not interact with each other in any way, because there are no significant intermolecular forces between their particles. Now, when the barrier is removed, the two gases can mix, but their potential energy remains unchanged. In other words, we cannot think of the mixing of ideal gases as lowering their potential energy. Rather, we just think of them as going towards mixing because of the dispersal of disorder, which brings us up to that specific word of entropy. So entropy is a measure of energy randomization or energy dispersal. I always like to say energy of disorder, so it's going towards more disorder. If you look at this is nice and ordered. However, when you remove the barrier, they're going all over the place, going towards disorder, towards randomization. We know that a gas at any temperature above 0 Kelvin has a kinetic energy due to the motion of its atoms. So when neon and argon are confined to their individual compartments, their kinetic energy are also confined to those compartments. When the barrier between the compartments is then removed, each gas, along with the kinetic energy that the gas has, becomes spread out or dispersed over the entire container, the larger volume. The mixture of the two gases has therefore a greater energy dispersal or greater entropy than when they're separate. So this has some kind of a kinetic energy. This has some kind of a kinetic energy. When you lift the barrier, it now is spread out over the entire volume, increasing that motion, therefore increasing the kinetic energy. So the tendency towards mixing gives us a higher energy dispersal. Now, going from a solid liquid to a gas, we know that the particles of our gas are all over the place. So the entropy increases from a solid to a liquid to a gas, because of the dispersal of the particles. So now we think of the effect of the intermolecular forces. So now we know that in the absence of intermolecular forces, two substances can mix spontaneously, which means without any extra work done, to form a homogeneous solution. But we know that solids and liquids are different because they have these intermolecular forces that are holding them tighter together. The entropy is more known for gases because gas particles are not attracted towards one another as strongly. So when we're thinking of solids and liquids, we have to think about all of our intermolecular forces. The energy changes in the formation of most solutions involve the attractive forces between the particles and overcoming them. In order for a solution to be formed, the solute and solvent have to mix. So basically, if you put salt in water, the salt itself has to break apart, right? Because the salt is like this. And then we have our water, which is like this. So first of all, these have to overcome so they can separate from one another. So do the water particles, and then they have to come together, being attracted towards one another. So there's three types of interactions that are happening. You have to overcome the solvent-solute interactions, solvent-solvent, and solute-solute. So here, if we think of our intermolecular forces, you can see a solution always forms if the solvent and solute interactions are comparable to or stronger than the solvent-solvent interactions and solute-solute. So if you have a solvent that has hydrogen bonding and a solute that has dispersion forces, they're not comparable enough to form because you have to overcome the solvent-solvent and solute-solute. And the solute and solvent interactions have to be wanting to be together. If you have a hydrogen bonding in water and a nonpolar substance for the solute, it is not going to be strong enough to break up the interactions between the water. So, Our dispersion forces, heptane and pentane, both nonpolar substances, dispersion can mix. Dipole will mix together, hydrogen bond, and ion dipole. So the intermolecular forces that you can see here that are within pentane and heptane are dispersion forces. Just like the intermolecular forces between these two are alike, so they will mix together. All three interactions that you can see up here in this diagram are of the same magnitude. So the substances that are soluble in each other in all proportions. When you have a substance that are soluble in all types of proportions because they have the same intermolecular forces is called miscible. The formation of a solution is driven by, we know, the tendency towards mixing, so greater entropy. So if solute-solvent interactions are weaker than those from the solvent and solute, the solvent molecules and solute interactions more strongly with molecules of their own kind. So for example here, the relative strengths of these interactions determine whether a solution will form. So the solvent-solvent interactions, the solute-solute, and then the solvent and solute. If the disparity is small, the tendency to mix results in the formation of a solution, even though the process is energetically uphill. If the disparity is large, a solution does not form. So if you consider mixing hexane and water, hexane is C6H6 and water is H2O. We know we have our dispersion forces and our hydrogen bonding. The water molecules have strong hydrogen bonding attractions to each other, but cannot form hydrogen bonds with hexane. So the energy required to pull water molecules away from one another is too great, and too little energy is required when the water molecules interact with hexane molecules. Therefore, a solution does not form when we mix hexane and water. Although the tendency to mix is strong, it cannot overcome the large energy disparity between the powerful solvent-solvent interactions and weak solvent-solute interactions. So in general, we can use the rule of thumb, like dissolves like, when predicting the formation of solutions. So similar kinds of solvents dissolve in similar kinds of solutes. So polar solvents, such as water, tend to dissolve many polar or ionic solutes. And nonpolar solvents, such as hexanes, tend to dissolve many nonpolar solutes. Because you have to think that, okay, if water has enough energy to split up, it's not going to go towards a solute that's super weak because it wants just as strong of the interactions. So the interactions that we see energetically have to be the same. So let's practice that. Is the following vitamin soluble in water or fat? So fat is a nonpolar substance. Water is hydrogen bonding. Now looking at vitamin C here in this diagram, would you think it's soluble in water, which is polar, or fat, which is nonpolar? Now the best way to determine that is to see, is vitamin C itself polar or nonpolar? How can we determine that? Well, we have 4 hydroxide groups, which therefore gives us our hydrogen bonding and a large dipole interaction. So this is polar. So would you think it's more likely to dissolve in fat or in water? In water, like dissolves like. Which molecule would you expect to be more soluble in water? Carbon tetrachloride or CH2Cl2? So let's draw it out. Carbon tetrachloride and then we have carbon, our 2 hydrogens, and our 2 chlorines. Now we know water's polar, has hydrogen bonding. Now, doesn't mean that the solute has to have hydrogen bonding, but it has to be similar in the types of strong forces. So we know that carbon tetrachloride is nonpolar. However, our CH2Cl2 is polar. So this will be more likely to dissolve in water. So we know that in our thermochemistry chapter, we examined the energy changes that are associated with different chemical reactions. Similar energy changes can occur when a solution forms, depending on the magnitude of the interactions between solute and solvent. Because again, in order to break apart the forces of the solute and the solvent, energy needs to be taken in. So when we dissolve sodium hydroxide in water, for example, heat is evolved. So the solution process is exothermic, because if you put salt in water, you feel heat. That means heat was generated, so it's exothermic. When we dissolve ammonium nitrate in water, heat is absorbed because it gets colder. This solution is endothermic. So when we're thinking of the energetics, we're thinking of solutions formed when they overcome all attractions between solute particles. They form when they overcome the attractions between all solvent molecules. And solutions form when the new attractions between solute and solvent particles are strong, comparable to their individual ones. So separating solute into its constituent particles. So when you're going to put salt into water, first thing that happens is to separate the solute into its constituent particles. This step, do you think, is this endothermic or exothermic? In order for these particles to split up, does it need energy or is it going to let go of energy? It will need energy, so it's always endothermic, and the enthalpy of the solute is always greater than 0, because energy is required to overcome the forces that hold the solute particles together. Let's think of solvent. So then after you separate your solute, you have to separate your solvent. So separating the solvent particles from each other to make room, right, for solute. Now, would you think this takes energy or releases energy? So this step is also endothermic, because the energy required to overcome the intermolecular forces of the solvent particles is always needed. So it's always endothermic, and the enthalpy of the solvent is always greater than 0. So just think, they're both close in contact, right? The particles want to be together, and we're trying to spread them apart so we make room for them to mix. In order to do that, we need to put in energy. So they're both endothermic processes. Okay, so now you have your solute particles that are spread out. You have made room in your water, so now you want to mix them. So mixing the solute particles with the solvent particles, would you think that's an endothermic or an exothermic process? So this step would be exothermic, because now you put these two together and they're going to release the excess amount of energy. The energy is released as the solute particles interact through intermolecular forces with the solvent particles. So sodium and chlorine separated into water will have an ion dipole intermolecular force, which is even stronger or close to strength as our hydrogen bonding, making it very, very energetically favorable. Now, according to Hess's law, the overall enthalpy change upon solutions we can call enthalpy of solution. So we've seen this before. So the overall will be the heat of the solute plus the change in heat of the solvent plus the change of heat of the mixture. This is always positive, the solute interactions breaking apart. Same with the solvent. And then mixing will always be exothermic. It'll be always negative. This brings us up to heats of hydration. So many common solutions, such as the seawater mentioned before, contain an ionic compound that's dissolved in water. So most of the time when we're thinking of homogeneous aqueous solutions, or a lot of the electrolytes that we've talked about in previous chapters, it's a salt dissolved in water. And a salt, we say, is an ionic compound. So in these solutions, we have the solvent and the mixture that can be combined in one single term called heat of hydration. The heat of hydration is the enthalpy change that occurs when 1 mole of the gaseous solute ions dissolved in water. The heat of hydration helps us kind of visualize more when we're specifically talking about an ionic compound. It's the sum of the negative of the lattice energy, which is also known as the heat of the solute, and the heat of hydration to give us the heat of solution. So, because the ion-dipole interactions that occur between a dissolved ion and the surrounding water molecules, again, if you have sodium that you separated in chlorine, water is going to hydrate the molecule to give us our solution. So, those ion-dipole interactions that happen are much stronger than the hydrogen bonds in water. So the heat of hydration is always largely negative. It's also always very exothermic for ionic compounds. So using the heat of hydration, we can write the enthalpy of a solution as a sum of the two terms. So you can write enthalpy of solution is equal to the enthalpy of the solvent mixture. We've known this. But now we can simplify this when we're talking about an ionic compound in water, because the solvent and the mixture are the heat of hydration. So we can say that the heat of solution is equal to the heat of solute plus heat of hydration. Now, heat of solute, will that be positive or negative? Positive, because it takes an energy to break apart our solute particles. And our heat of hydration, will that be positive or negative? Negative, because it's exothermic, mixing together the solvent and the mixture, hydration through the ion-dipole interactions. So for ionic compounds, we know that the heat of the solute is the energy required to separate the solute into its constituent particles. So basically, we know that you have a crystal, which is called the crystal lattice, and you put in energy to break apart the solute particles. So technically, the heat of the solute is actually the negative solute's lattice energy. Since lattice energy is the amount of energy that's needed to take the particles together to form a crystal, or they needed to break them apart. So it's another way of defining our heat of our solute specifically for an ionic salt. So for ionic aqueous solution then, the overall enthalpy of solution depends on the relative magnitudes of the heat of the solute and the heat of hydrations, where we have different scenarios possible. For example, you could have your heat of solute less than your heat of hydration. What do you think would happen then? So the amount of energy that's needed to separate the solute into ions is less than the energy given off when the ions are hydrated. So then the heat of solution is negative, and the solution process is exothermic. Solutes with negative enthalpies of solution, including lithium bromide, for example, or potassium hydroxide. When these solutes dissolve in water, the resulting solutions feel warm to the touch. We have another scenario where, what if your heat of your solute is greater than your heat of hydration? So now that means that the amount of energy that's needed to separate solute into its particles is greater than the energy when the actual hydration happens. So it's really positive, and the solution is endothermic. Solutes that form aqueous solutions with positive enthalpies of solution include ammonium nitrate, silver nitrate. So when they dissolve in water, it always feels cool to the touch. So think, when it's endothermic, it's going to feel cool to us because it took in the energy to cool down. When it's exothermic, it's going to feel warm to us because it warmed up through letting go of heat. Another last possibility here is when they're equal to each other, very close. So the amount of energy required to separate the solute into the constituent ions is roughly equal to the energy given off when the ions are hydrated. So the heat of solution is approximately 0, and the solution proceeds neither exothermic or endothermic. So basically it would be like plus 0.9 or negative 0.1, so really close to 0. Let's practice. When ammonium chloride is dissolved in water, the solution becomes cooler. So we took ammonium chloride, NH4Cl, and dissolved it in water. And it cooled down. So does that mean that the dissolution is endothermic or exothermic? Well, if it feels cool to us, that means it took in energy to decrease the temperature. And the decrease in temperature is because the water took in energy from the dissolution of ammonium chloride. Therefore, it is an endothermic process. What can you conclude about the relative magnitudes of the lattice energy of ammonium chloride and its heat of hydration? So the dissolution is the process where solvent molecules break into ionic compound particles. Lattice energy is the amount of energy released when gaseous ions combine and form 1 mole of the ionic compound crystal. Hydration energy is the amount of energy released when 1 mole of the ionic compound is dissolved in its ions and surrounded by water. So if you have a greater value of the lattice energy, then more is the amount of energy needed for dissolution. So the reaction becomes endothermic. Since we have an endothermic reaction, that means we had more energy needed to break apart the particles. So as a dissolution of ammonium chloride is endothermic, that means the relative magnitude of the lattice energy of ammonium chloride is greater than its heat of hydration, because it's endothermic. So we needed a lot of energy. Therefore, it means that the solute was very, very highly endothermic, so the lattice energy is greater than the heat of hydration. Sketch the qualitative energy diagram. So the dissolution of ammonium chloride is an endothermic reaction, and it absorbs energy. So when we want to do a qualitative diagram, we have a little plot here where we have the energy and reaction progress. And you have your reactant and then your products. So you want to see that the energy diagram is endothermic. So that means that the energy of the products will be higher than the energy of the reactant. So you make your little loop because they first have to overcome that energy, and then you're done. So basically, going from reactants to products, you need energy. So you always start greater than 0. And then if it's endothermic, the products will be higher. If it's exothermic, the products will be lower. However, there's always, and we'll talk about this in our kinetics chapter, a barrier for these energies to overcome. That's called an activation barrier. It's the minimum amount of energy that's needed to overcome the particle interactions and form products. The difference then from the products to the reactants give us our heat of hydration. So why does the solution form? What drives the process? So we know that the enthalpy and entropy are two driving forces, the energy and then the tendency towards mixing. Chemical reactions always proceed in the direction where enthalpy change is minimum and entropy is maximum. So we're using little energy, but we're going really towards disorder, tendency towards mixing. So chemical reactions want to mix and not use a lot of energy. Enthalpy is a driving force for exothermic reactions because they release energy, they don't need it. And entropy is a driving force for endothermic reactions as the reactions absorb energy to proceed to products that have higher energies than reactants to go towards the greatest mixing process. So specifically here, the dissolution of ammonium chloride is endothermic. We already discussed that. So the enthalpy change is maximum. Because it's endothermic, it needs a lot of heat, so delta H is really, really high. That means that the ammonium chloride, when dissolved in water, degree of randomness also increases. So we have a high entropy increase. Therefore, the dissolution of ammonium chloride forms a solution even though enthalpy change is at maximum. Again, you always want the enthalpy change to be minimum. But because these break apart, it's going towards mixing, and that entropy increase is what drives a reaction forward. Okay, let's figure out the next one. So we have here lithium iodide that has a lattice energy of negative 7.3 times 10 to the second kilojoules per mole, and a heat of hydration of negative 793 kilojoules per mole. So you have your heat of lattice, heat of hydration. Find the heat of solution for lithium iodide and determine how much heat is evolved or absorbed when 15 grams of iodide is completely dissolved in water. Okay, so we know that the heat of solution is equal to the heat of the solute plus heat of hydration. We know heat of solute is negative heat of the lattice energy, and we also know that heat of hydration is negative. So, do we have enough information to solve for the heat of solution? Yes, you would plug in your values. So you have your heat of your lattice and your heat of hydration. Now, from there, how can you solve for just the heat when you have 15 grams of lithium iodide? Now, I'm going to let you do this on your own as an engagement question, and then you will submit it to me at the end of the day. So just a little bit more for this section here. Solution equilibrium. So what does that even mean? So again, going back, the dissolution of a solute in a solvent is an equilibrium process. Because you have your salt crystal, and then they break up, the water molecules make room, and then they separate. Why will this be in equilibrium? Well, we know that they dissolve, the water takes them in, and eventually both is happening at the same time. So when sodium chloride is first added to water, sodium chloride and chloride ions dissolve. As the solution becomes more concentrated, meaning it's not water anymore, you added more salt, some of the sodium and the chloride ions recrystallize to form solid sodium chloride. So then when the rate of dissolving, so the rate of dissolution, equals the rate of recrystallizing, reforming the sodium chloride salt, we've reached dynamic equilibrium. So at first, the rate of dissolution always exceeds the rate of recrystallization. But as the concentration increases, the rate of recrystallization increases to then eventually reach our dynamic equilibrium. And therefore, you will see that sodium chloride equation always has our double arrow when forming into the ions. So a solution in which the dissolved solute is in dynamic equilibrium with the solid that's undissolved, a solute is saturated solution. So when they're in equilibrium. So if you add any more solute to a saturated solution, it will not dissolve. So for example, if you had 36 grams of sodium chloride, that will completely dissolve. If you add any more, it will not. Saturated. So then a solution that contains less than the equilibrium amount of a solute is unsaturated, which means that if you wanted to add any more solute into an unsaturated solution, it will dissolve. Then we have one more process of that, which is going up. So a supersaturated solution can form if one contains more than the equilibrium amount of solute. So supersaturated solutions are unstable, and the excess solute normally precipitates out of solution. Because there's so much excess, it usually comes up to the surface. For example, here, the precipitation from a supersaturated solution. When a small piece of solid sodium acetate is added to a supersaturated solution. So here we have a supersaturated solution, and we add a small piece of sodium acetate. The excess solid precipitates out of solution to then form this crystallized process. Taking that into practice. So, a solution contains 25 grams of sodium chloride per 100 grams of water at 25 degrees Celsius. Is this solution saturated, unsaturated, or supersaturated? Well, first you have to understand what the solubility of sodium chloride in water is at 25 degrees Celsius. So you would have to look that up. Well, the solubility of sodium chloride at 25 degrees Celsius in 100 grams of water is 36 grams. So if you have 25 grams that you want to put into the solution under these conditions, do you have a saturated solution, unsaturated, or supersaturated? You have an unsaturated solution because you're below the equilibrium amount, meaning you can still add some solute and it will dissolve. Now, let's think of the temperature. Now, we've talked about the equilibrium, the dissolutions, and the recrystallization. Will temperature change that? Well, the solubility of solids in water are highly temperature dependent. I always like to think of iced tea and hot tea as an example, or even iced coffee and regular coffee, because we know how much I love coffee. If you put, it's a little easier to see with tea. If you put sugar into a hot tea, can't really see it after a while because it mixes really, really fast. Now, iced tea or cold tea, you can actually see the sugar particles on the ice because it doesn't dissolve as well. So the solubility, for example, of potassium nitrate at room temperature is around 37 at 100 grams of water. Now, if I crank up the temperature to 50 degrees Celsius, because you're adding energy, right? So if you increase the temperature, you're making it hotter. So you're giving the particles more energy to break apart from one another. So do you think that means that you can dissolve more and the solubility increases? Yes. So at 50 degrees Celsius, the solubility of the potassium nitrate in 100 grams of water goes all the way up to 88. So that's a big difference. From 25 degrees Celsius to 50, you have almost double the amount that you can dissolve. The solubility of most solids increases with increasing temperature. So here, for example, you can see the potassium nitrate, the green, that it's increasing as you're increasing the temperature. Potassium dichromate, potassium chlorate, potassium chloride, lead 2 nitrite, calcium chloride, sodium nitrate. Sodium chloride, not as much. Then what else do you notice? Well, you also notice that the sodium nitrate actually decreases as you increase the temperature. So it's for most of them, but not all. Now, a common way to purify solids is through recrystallization. In this technique, enough solid is added to water or any other solvent to create a saturated solution at an elevated temperature. So again, you have a really, really high temperature. You're adding much more solid to a solution that's already at equilibrium. So then as the solution cools, it becomes supersaturated because you have a lot more than you were allowed to at your equilibrium. And the only reason you were allowed to add so much was because you added heat. So then when you cool it down, it becomes supersaturated and the excess solid precipitates out of the solution. The crystalline structure tends to reject impurities, resulting in a pure solid. So kind of to show you the temperature dependence of the solubility of solids is how to make rock candy. So when you prepare a saturated sucrose, so table sugar solution, at a really high temperature, and allow a stirring or stick to dangle into the solution for several days. So basically you have this cup and you add a bunch of sugar that are above the equilibrium, but it's heating. And if you add this stick and you leave it in there for a couple days, the super saturated solution that is created crystallizes onto that stick, and that's how you make rock candy. So thinking of gases is a little bit different. So the solutions of gases dissolved in water are very common. Club soda, for example, is a solution of carbon dioxide and water, and most liquids exposed to air contain dissolved gases from air. So the solubility of a gas in a liquid is affected by both the temperature and the pressure. Since it's a gas, we have to also think about the pressure of the gases. When heating tap water on a stove, before water reaches its boiling point, you see that small bubbles develop in the water, right? Before you actually see them come to the surface. Those bubbles are the particles that are dissolved inside the liquid. So it's the gas dissolving in the liquid are the little bubbles that you see when you're warming up or trying to boil water. So even in your beaker, you see the little bubbles before they go all the way to the surface. Those little bubbles are the dissolved gaseous particles in your liquid. Now, after a while, you'll see the larger bubbles form, which is the dissolved that's coming out of the air into the heated solution. So the solubility of a gas in water decreases with increasing temperature. Another good example of this is warm soda versus cold soda. Now, warm soda, right? What happens when you have a soda in the fridge that you open up and then you left out a soda in warmer water and you open it? Well, warm soda bubbles more than cold soda because carbon dioxide is less soluble in warm water solutions. So warm soda bubbles more when you open it. More carbon dioxide comes out of the solution at room temperature than at lower temperatures because the gas is less of a solute at room temp. So if you think of the relationship between gas solubility and temperature, it's the reason that you have more bubbles in warm soda than in cold. So more carbon dioxide comes out of these solutions at room temperature than at lower temperatures because the gas is less soluble at room temp. The decreasing solubility of gases with increasing temperatures is also the reason, for example, that fish don't bite in warm lakes. The warm temperatures result in a lower oxygen concentration. With lower oxygen levels, the fish become lethargic and do not strike as aggressively. So less bubbles are inside when you have warmer water than when you have colder water. So it's less soluble in warmer temperatures. Now, if we think of the pressure, the higher the pressure of a gas above the liquid, the more soluble the gas is in the liquid. So the solubility of a gas depends on pressure. In a sealed can of soda, the carbon dioxide is maintained in a solution by a high pressure of carbon dioxide within the can, right? Because it's closed. When the can is open, this pressure is released and the solubility of carbon dioxide decreases, resulting in bubbling. When you open this, some of the particles go out of the can and some go back into the solution, therefore decreasing the solubility. The increased solubility of a gas in a liquid can be understood by thinking of a cylinder of water and carbon dioxide. The first cylinder represents an equilibrium between gaseous and dissolved carbon dioxide. The rate of carbon dioxide molecules entering the solution equals the rate of molecules leaving the solution. Now imagine if you decrease the volume. We've learned from Boyle's law what happens when you decrease the volume. You are increasing the pressure. So now in our second cylinder, the pressure of carbon dioxide increases, causing the rate of molecules entering the solution to go up. Because you have less space, the pressure increases, so more molecules are going to go into the liquid. So the number of molecules in solution increases until equilibrium is reestablished. Now in the third cylinder, you can see that this process will continue until the equilibrium is reestablished. The way that we quantify the solubility of an increasing pressure is through Henry's law, where the solubility of a gas is equal to the proportionality constant, Henry's law constant, which depends on the specific solute and solvent, as well as the temperature, and the partial pressure of the gas. So the equation shows that the solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. Meaning if one goes up, the other will go down. So let's look at these two questions. What pressure of carbon dioxide is required to keep the carbon dioxide concentration in a bottle of club soda at 0.12 molar and 25 degrees Celsius? So if we're looking at pressure and our solubility, we look at Henry's law. So we have the solubility, club soda has carbon dioxide in it, is equal to the Henry's law constant times the partial pressure of carbon dioxide. You are looking for the pressure. So the pressure of carbon dioxide is equal to the solubility divided by your Henry's law constant. Now you have to look up Henry's law constant. You are given the solubility for 0.12 molar. So carbon dioxide is 3.4 times 10 to the negative 2. So you have 0.12 molar divided by 3.4 times 10 to the negative 12 molar over atmosphere. Now what you notice is your molars cancel, your atmospheres move up, and you will get, if you look at your units, the appropriate units for pressure, which will be 3.5 atmospheres. So you need the pressure to be around 3.5 atmosphere in order for the solubility to be 0.12 molar for carbon dioxide at this temperature. Now try it on your own. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmosphere. So try this.